Okay, hi everyone, can you hear me? Okay, great. So we're going to get started. So I'm Aaron Noel. I'm at the Jet Propulsion Laboratory, and we even got video. There's Stephanie. Hey, Stephanie, can you unmute and try to say hello?
Yes, can you hear me?
Woo.
I'm very loud. I can sound.
Technology at work, it's amazing.
Okay.
Right, so we're going to try to give you an overview of instrumentation, and that is being developed mostly for life detection, but obviously has sort of direct application to abiotic chemistry. But so to kick that off, we're going to briefly divert and talk about what should you do, or what you would ideally do with samples when you get them in the lab. And so Heather Graham is going to come up and give us a brief overview of how return sample analysis looks like when you're talking about doing the most detailed chemical analysis you could hope to do. So.
How's this sound? Sound okay, guys? I'm really honored to be part of the abiotic context for life detection with in situ instrumentation, since I'm only going to talk about one of those three things. Let's see. Yeah, so I'm going to be talking about technologies that can be used for life detection, but weren't necessarily used for life detection in the context of this work. I'm going to be talking about the high fidelity analyses that we were able to do with returned samples from an asteroid. I don't know what the general familiarity in the room will be for the OSIRIS-REx mission. You often just hear it referred to as an asteroid sample return mission. But it's important to know that in the tradition of all great NASA missions, it's mostly a tortured acronym. So the many things that the OSIRIS-REx mission did were return and analyze samples to tell us something about pristine extraterrestrial materials that can help us understand the origins of planets and ultimately possibly the origin of life. But it also did a lot of spectral interpretation of that asteroid while it was there. It also identified resources that were there, and by resources we mostly mean minerals and elements. And it did that in situ, as well as I'll show you data to compare what it looks like when you get it back in the lab. It had security jobs as well that it did, which was to measure thermal properties of the asteroid that tell us how likely it is to come into contact with our own planet or get near to our own planet. And it examined the regolith at many scales using a variety of kinds of imaging devices to tell us what this looks like. The OSIRIS-REx mission launched. It took 2 years to get there, so that gives you an idea of what it means when we say near Earth. Of course, the objects that we're talking about when we talk about ocean worlds are much farther than that. But then it also spent 2 years looking at that asteroid. So thinking about what Kevin said earlier today about how you really need all of that context to understand your sampling location, that is, of course, of super importance, even when you're bringing the sample back home. That's an important lesson for in situ as well as returned samples. So we have a wide array of instruments that were on the orbiter that spent 2 years examining the asteroid. So we had different kinds of cameras. We had an altimeter. We had a student project that looked at elemental abundances. We did a lot of thermal flux and spectral measurements. We had a thermal emission spectrometer and looked at the albedo and other spectral information. So this was a lot of information to tell us things about the elemental composition, the mineralogy, and the surface roughness, as well as the altimetry of the object. Because what we were doing as part of that 2 years, thinking about what Shannon said this morning, we had 2 years to argue about where we were going to sample. So that's much more time than Orbilander was giving themselves. When we did do that, let's see if I can make this work. For the purposes of sample return, the most important instrument in this array of things that I'm showing you is the TAGSAM. It's basically a Roomba on a stick on a spacecraft. And it contacted the surface of the asteroid, which ended up being very dusty. and very light and very low gravity. And it pulled up a whole lot of material. In fact, it pulled up a lot more material than we had set as our minimum that we wanted to get as part of this mission. We brought back 121.6 grams of sample. And our minimum for that would have made us happy was 60 grams. So we felt pretty happy about that. In fact, there was so much material in these trays that were part of that Roomba that I showed you that it even had a hard time closing. So there were different operations that they had wanted to do as part of the mission, but they ended up just closing it up and putting it in the capture vessel. It came back to the lab, and so we have 66 plus instruments that are slated to examine these samples, that 121.6 grams. And as you can see, some of these are things that would be really, really hard to fly. So this is where we stray from the promise of in situ instrumentation. I think it'd be really hard to fly an accelerator mass spectrometer or ZANES. And these are the kinds of measurements that we were hoping to do with the samples. I also wanted to make sure everyone knows that now the samples have returned for us, but the spacecraft has kept going. And it is now looking at a different asteroid that it is also considered to be near Earth and is actually a much higher probability of coming close to Earth. And they're doing the same sort of spectral characterization of that planet and trying to understand its trajectory as well. So, you know, maybe there's hope for they'll come for us. So the OSIRIS-APEX mission does keep going. Now, what are we doing with these 66 plus instruments? I wanted to, there's many analyses that are happening with these samples. There are six groups, 5 of which only look at elemental compositions, mineralogy, things like that, just geology questions. And so there's only 1 group that looks at organics. And here's all the jobs that we're doing. I hope you were dazzled by that animation. It took a long time for me to figure out how to make it happen. Each one of these pink boxes that you can barely see is a different analyte of interest. Each one of these squares that you see is a different instrument doing that analysis. All of those arrows that you see going everywhere, and we'll zoom in to look at these in a little bit more detail, are pathways from the bulk rock that the organic analysis group was given to different people who are doing those analyses. And each one of these things that you see in blue boxes up above here, those are all different kinds of sample processing. And so you can see this is a large orchestration of activities so that some of these sample processing activities serve many different analyses for many different analytes of interest. Let's see. So here's a way that we can zoom in and start to see that, again, this is just organic analysis. There are 5 other working groups doing very similar activities, but with very different kinds of instruments. But here's all of our analytes of interest that we're thinking about. And let's see. Oops. Let's see if I can get it to zoom in. There we go. So what you can see is that from that 120 grams, our organic analysis group got 7 grams. Now remember, 70% of the asteroid is saved for the future for our kids and grandkids who are going to invent even better things to do analyses on that. So we got 7 grams to answer part of the 11 hypotheses that directed all of the analyses that we do. So we had to share a lot of this material. And I also wanted to say that when we are working with solid materials, all of our solids are saved. And they are often routed back over to the folks who are doing the geologic work. Because if there's nothing about the way that we process that sample that would be a problem for that analysis, it's best used to keep going. And that way we have a full understanding of that rock or lithology that we're looking at for this. And there's several different lithologies that we've identified as part of the material brought back from the OSIRIS-REx mission. So you're probably wondering, how do you start to conduct an orchestra like this? A lot of this work came out of different kinds of dress rehearsals that we had, which we called sample analysis readiness tests. So this would be the kind of thing where we take a similar kind of meteorite that we thought we were going to be analyzing, and we would distribute it amongst the groups, and we would work on optimization of our methods. And these are the kind of activities that actually took years. Every analysis that was part of that big array of analyses that I showed you had to be based on a published paper, had to demonstrate its utility. There was nothing, necessarily experimental about any of this. That angers some people because in the 6 years since that was all set in stone, maybe there were new methods developed, but that's what we promised ourselves we were going to do with this. And we did that. And if you have a new and better method that you made, then you can ask for some of that sample because it's all stored down at Johnson and anyone in this room can apply to do analyses on it. So we did all these different kinds of extractions, different kinds of separations, different kinds of particle separation, looked at specific mineralogies, things like this, to try and optimize all of those different analyses that we do to understand the effects that our analyses have on the samples as well. Because remember, our material may go downstream to someone else who's going to do a follow-on analysis. So we did lots of these kind of activities, and these were actually really interesting and fun. I'm showing you some of the flow charts that we did for when we were actually looking at the effects of micro XCT scanning on the rocks, because we wanted to understand their permeability and porosity and their internal characteristics. How then did that scanning affect the organics that are in this rock, considering this is about 5% carbon. So we did a lot of work on that to make sure that that scanning wasn't going to cause a problem. So these are the kinds of things you can do when you are bringing things back. You can have that wide array of analytes that you can measure at really high, with really high fidelity, and you can pass along all of that material along many different pathways. We also tried to really understand how the potential for contamination might have entered into this. So we did a lot of work looking at witness materials, which I'm showing here, witness plates that were part of the spacecraft itself, part of the spacecraft assembly areas, and part of the analytical facilities. So we understand the exposure that this materials had as it went along the way. Now, I only have a little bit of time left to show you results. I'm sorry about that, but I thought you'd be interested to see. Here is the elemental abundances that we've been able to get. And we can, because we have an elemental analyzer that was on the spacecraft, we can compare with that student project and understand ways that that can be better developed, and also understand a little bit about what this means for the measurements we're going to make at Apophis in this next phase of the OSIRIS-REx mission. Since this is a group that's primarily probably going to be interested in organics, what I can tell you about Bennu is it has a lot and many different kinds. And this is a measurement that would be very, very hard for you to do in situ to understand the 16,000 individual compounds that are there and the over 175 volatiles that are degassing from this asteroid right now as it sits in a glove box down in Houston. We can look at the rich chemistry of the insoluble and soluble organic phases with the kind of instrumentation that we have in laboratories back home. And this is a paper that just came out where we're talking a lot about the surprising amount of nitrogenous compounds that there is in this, and the sheer amount of ammonia that was in this sample. Big fun things to think about is 14 of the 20 proteinogenic amino acids are in this, as well as all 5 of the nucleobases that are part of our lineage. When we think about how the instruments on board the spacecraft compare to the kind of measurements that we're able to make in the lab, we could give general categories of minerals that we thought we were seeing with the thermal emission spectrometer on the asteroid while we were in orbit. And so we had all of these categories of things that we thought we had saw. But then when we get them back home, we're able to look at really fine scale things like the bulk isotopes of those materials. We can build an understanding of the history of the asteroid by looking at the relative abundances of all of these minerals and associated elements to tell us something about how that body has changed over time. And this has helped us understand the evaporation event and the alkaline nature of the early water that was probably part of the parent body that this broke off from. And then once we get it back into the lab, we can take a look at that sample and compare it to similar things that we see here on Earth, like this Trona hand sample, and start to build an even better picture of what has happened during that asteroid's life, and accompany that with the kind of instrumentation that would be very hard to put on the surface of that asteroid. So I realized that this meeting is a little bit of a crazy idea festival. So I'm really honored to be probably the craziest idea, which is while we're talking about all of these exciting things we could do at Ocean Worlds, don't forget, you can bring it back. And depending on the hypotheses and the kind of measurements you want to do, that might be trade space that's honestly available to you if you want to be able to use the kind of 66 plus instruments that we have used as part of our organic analyses and mineralogical exploration of this asteroid. And certainly, I like this graphic that Queenie Chan put in a paper. We have a long history of bringing back rocks from space, and we continue to bring back bigger and bigger chunks from farther and farther away, primarily using the kind of robotic sampling that we've seen in the last decades. And I think that's all I had to say. So sorry I went over. Oh.
Thank you, Heather. That was perfect. That was exactly the sobering beginning that we needed for this. Let's see if I can bring up the other thing again. No.
Aaron, do we have time, you think, to entertain any questions for Heather before we move into the next segment?
Well, if you people want to try to do that while I fuddle with this, that would be good.
I can't see hands, so whoever would like to ask a question, assume there's a microphone in the room. And thank you, Heather, for your great presentation. I mean, I think this is just a wonderful representation of the breadth of science that we can do with an incredible suite of earthbound instruments for a sample return mission, and really complements and provides more of a foundation for the exploration that we can do in situ. So really appreciate you taking the time and being there today.
Great. So there were two questions in the room that I saw. I'll start with Shannon.
Thanks, Heather. That was a really great talk. I was really excited by your fancy flow chart and the SARTs that you did. Mm-hmm. Because one of the things we talked about for Enceladus Orbulander was the importance of being able to conduct measurements in concert if possible. So like what kind of sampling processing systems would you need to pass a little bit of sample to one instrument and another so that they're both, acting on the same sample that's acquired. So my question for you is, can you see any lessons learned from that in situ on Earth experience that could be translated to what we're going to have to do robotically at those places to make most efficient use of the sample?
Yeah, I think all of that dress rehearsal was not wasted time. Because we learned things about, oh gosh, you did what? Oh no, that totally ruins it. You used what kind of mortar and pestle? Oh geez, now I can't use that for my measurement. And so all of that stuff had to be recorded, because we would think of like, well, when we do something in organics, you inorganic people, you don't care. And then it turns out, something that we're using in the lab becomes a huge contamination potential for them. Like just getting all the different groups to understand what contamination means to my group was very hard. I think for something like what you're talking about, it's easy to think about this as all just practice, but it's not. It's really learning. It's really refining things. And we were constantly going back into that document that guided everything that we did. It sounded like those papers that we all wrote were a promise to each other. But when you start to think about how you're going to link all those papers, it becomes really, really important. I know that at the time scale that you're often developing these things, you don't get time for that practice. And so if there was a way, as you were developing your suites of instruments, like you showed us, to start doing cross comparisons and sample handoffs between all of those things as you're developing those individual instruments, that would probably be the way that I could kind of see an analog activity that from what we learned as part of SART being something that you can make part of your practice. I hope that helps. Yeah.
Our hope is to get to a discussion
Oh.
at the end, so let's save the next question.
Okay.
And so but please come back to that.
Yeah. Save your cube, Ashley.
Okay, so I think next up, Stephanie is going to sort of start us off on this presentation. And, Stephanie, I'll be here clicking your slides. I don't think you have that power. So just let me know when you want the next slide.
Okay, yeah, I don't have that power. And my vision was to hand off to you, like kind of tag team to keep the presentation interesting. So
sounds good.
Yeah, thanks for bearing with me in virtual form this morning. I really miss seeing so many amazing colleagues there in the room, but I had to hold down the fort over here at Goddard. For those of you who don't know me, my name is Stephanie Getty. I used to be in the lab, and now I am mostly a manager. So thank you also for allowing me to be an interloper on your workshop today. But I have really enjoyed being part of this community for many years, and again, it's great to be with you today. And it's been great to work with Erin on this session. So thank you, Erin, for being an amazing partner on this. So we're going to go through a little bit of the historical perspective and current and upcoming events in situ instrumentation. And the focus here, of course, is on providing the abiotic context for measurements that we make. But a lot of the instruments that you're going to see have do not have a very crystallized dividing line between abiotic measurements and biologically relevant measurements, right? And so I think being prepared for discoveries when you send an instrument far from Earth into a poorly understood environment is a really good principle. So you're going to see a lot of that in what we have coming up. Let's go to the next slide. Just to set the stage a bit, I mean, we've seen such an explosion of discoveries over the past decade and of course, decades. And I just wanted to highlight a few of them here. We just heard about the incredible breadth of investigations that are able to be done by a really far-reaching, highly capable team on Bennu samples returned by OSIRIS-REx. And of course, that's complemented by the Hayabusa missions that also returned asteroid samples, and comparisons in the lab between our meteorite databases and what we're seeing from these return samples is just, really enriching our understanding of the early solar system. Of course, Mars continues to be a really fertile environment for exploration. And so we've seen a lot of signatures, a lot of clues, a lot of building blocks on Mars. Most recently, the discovery by the Curiosity rover and the SAM instrument on board of these structural materials, these long chain hydrocarbons that in life as we know it, provide structure and encapsulation of environments within biological systems. Of course, congratulations to the Europa Clipper team on a successful launch. We're so excited to see that on its way, and we'll talk a little bit about the relevant instrumentation there. Of course, Dragonfly and the development of this rotorcraft and an incredibly capable payload to go to the surface and explore multiple environments on Titan. you know, continued interest in Ceres, as we know, as potentially a dwarf planet, definitely as a dwarf planet, but potentially, you know, a region of the solar system that is a snapshot of this gray zone between prebiotic and biologic or habitable environments in our solar system. Of course, this is all complemented by field work, going to extreme environments on Earth and understanding the limits of biology on our home planet. And then this should all feed into, this is a great underpinning for going out with James Webb, as we're doing now, James Webb Space Telescope, and onto the Habitable Worlds Observatory in the future, and Roman Space Telescope in between, to really explore exoplanets that we can't, you know, we don't expect to be able to touch, but are important to our understanding of kind of the limits of habitability across the universe. So next slide, and I think I am talking too long. What we should do, Erin, probably is wrap up, what, at 11:15 at the latest with this presentation so that we can get to our panel.
I think that's the plan. Yep.
That's the plan. Great. So, so I won't spend a lot of time on this slide. This is an old slide, and many of you've seen it before. But just to show the gradient, the spectrum of signatures, you know, that we consider and have continued to consider as you know, the important framework of being able to tell the story of what is a biosignature, and what is our confidence level in identifications that we make from, you know, understanding kind of the raw materials and the nutrients and the food, all the way up to kind of informational polymers that provide the complexity for coding the details of biology. So let's go to the next slide. All right, the only point I'm going to make here is that you know, I have two slides here. One is focused on how we are building on our understanding of atmospheres and exospheres throughout the solar system through a series of missions and increasingly sophisticated instrumentation and increasingly sophisticated understanding of the underlying science to reveal the mysteries of planetary environments from an orbital or flyby platform. Go to the next slide. Complemented by, you know, important in situ, on surface exploration of planetary environments, and so, you know, a lot of the you know, the incredible work that has gone into these fleets of missions and the instrumentation underlying, they build on each other, the discoveries build on each other, and then as a community, our task, right, is to envision what comes next and what we can do to answer new questions that are prompted by measurements that are made, that come before us. So let's go to the next one, and we're going to start bouncing back and forth. But let me start here with Cassini-Huygens. So we're going to take you through some of the previous missions and the instrumentation and the capabilities that have flown before, just to review what we've done as a community, what, you know, the discoveries and tantalizing indications, as was seen in the, you know, the rarefied plume material at Enceladus by the Cassini mission and the ion and neutral mass spectrometer, and how that has inspired, you know, of course, our current and future missions. So you can see here, you know, our when we launch a spacecraft like Cassini-Huygens, going far from the planet Earth, of course, we want to build something that is, you know, flexible to discoveries and capable of, you know, of making foundational measurements that prompt the next set of questions. And so, you know, over the 13 years that Cassini orbited the Saturnian system, of course, had the opportunity to not only discover the plumes of Enceladus, but also, you know, touch some of that material. And so you can see an example, you know, kind of artistically rendered here, but also accurate mass spectrum on the lower right-hand side that provides, you know, great insight into the composition of that plume, and also, you know, teases us into wondering, you know, what those unresolved organic signatures might be. And so that drives our desire for pushing forward into future capabilities of instrumentation. So let's go to the next slide, because I want to also highlight of course, Cassini carried the Huygens probe, which descended through the atmosphere of Titan in 2005, and carried a gas chromatography mass spectrometer that was able to resolve with those capabilities another, this mass spectrum that started to give us insight, over a limited mass range, and with reasonable mass resolution, but also for the first time so far from home, really implementing and demonstrating the capability of this additional separation element of the GC on the front end, and revealing now for the first time just the start of our understanding of the complexity of Titan's atmosphere that will be really fleshed out and given much more detail over the coming decades as we send Dragonfly out there. So I think I'm going to hand it to you now, Aaron, with the next slide. If you
Yep, I'll do the next couple.
Great.
Thank you. And so, right, I mean, I think what Stephanie has shown is that there's a lot of mass spectrometers in situ analysis, and that's for good reason. They obviously provide you a tremendous amount of bang for your buck in terms of deciphering what's there. But there have been other missions that are also pushing other sorts of in situ chemical analysis. One is the Phoenix mission, and sort of in terms of, if you think about implementing Heather's flowchart, you've got to go, from sample in all the way through data out. And Phoenix taught us some important lessons there about sample handling being hard, and that the detailed chemistry matters. So I'm going to focus on the two most relevant chemistry instruments for a moment, which were the microscopy, electrochemistry, and conductivity analyzer, and the thermal and evolved gas analyzer. And so TIGA was a really cool instrument. It's in the bottom right there. It was a combination of differential scanning calorimetry coupled to a mass spectrometer, so you could see the phase changes in minerals or solids, and then also analyze the volatiles as they came off. Unfortunately, other worlds are tough. So Phoenix wanted to go and find ice and look what was in there, but it turns out ice cemented soil doesn't fall through a screen. It just sits there, and it frustrates you. And so that was a big disappointment in Phoenix. But I think sometimes that's the end of the story to people. But it's important to remember that, okay, once that ice sublimates away, it sort of becomes grainy, and it does go through your screen. And then the differential scanning calorimetry and analysis allowed this confirmation of calcium carbonate, which is a very important part of the Mars story as well. But so then the thing that was maybe more of an afterthought at the beginning of the mission, but then became to play a really important role, was a bit of wet chemistry, which is something we'll be talking about pushing into for in situ exploration. But the wet chemistry lab, which was the electrochemistry part of the MECA instrument, was a cute little sort of freshman chemistry experiment beaker. The bottom part there has electrochemical sensors embedded in the walls. It has a little drawer that shoots out and accepts the regolith and then dumps it into the beaker. And the primary result from WICL was the discovery of perchlorate on Mars. And that sort of, that getting that detailed soluble chemical analysis, not just sort of a mineral or elemental analysis, is what allowed this whole unraveling of the extremely interesting sort of Mars chemistry story, which is that, yes, there are plenty of organics on Mars, but if you happen to, heat them in the presence of perchlorates at high temperature, as we tend to do with pyrolysis, you're going to end up with chlorinated hydrocarbons. And those are analyzable, but you need that whole story to be able to tease it apart. And so that's kind of the power of pushing on to additional sample handling, additional types of analyses in addition to the mass spectrometry. Actually, so Stephanie, you want to go back on Curiosity?
Yeah. Actually, so that is a great connection point, right? Because at the time that Whipple was identifying the perchlorates on Mars, the SAM instrument was being developed at Goddard with important contributions from France and from JPL and responding, right? Having to respond in the middle of development to this discovery of this salt. And, it just goes to show how important these missions complement each other and how you are able to incorporate discoveries from prior missions into, preparation for operations and some of the analog samples that you run through instrumentation. But yeah, but let me turn to Curiosity for a bit now. Well into its 12th year of operating at Gale Crater on Mars. What an incredible rover. This is like a artistic depiction, but if you look at the real selfie from the last time that the rover took a selfie, it looks very rugged, like it's been out in the field for many years, and it's very impressive. So these are some of the goals that the mission set out to address, assessing this region of Mars surface, Gale Crater with Mount Sharp in the center, assessing biological potential, geology and geochemistry, the role of water, and of course the surface radiation environment, just highlighting how interdisciplinary a payload needs to be, right, to tease out the meaning and the interpretation of the discoveries that we make in the context of a given environment. So let's go to the next one. Right, so here's SAM. It is it has been described as a large microwave oven. I don't know if microwave ovens actually come in this size anymore, but just goes to show how long it's been. So SAM consists of, at its heart, a quadrupole mass spectrometer, a gas chromatograph, of course, building on Huygens heritage. That's a 6-column GC with a lot of capability and complementary chemistry inherent there. The tunable laser spectrometer from Chris Webster's group at JPL, a gas processing system, and a sample manipulation system. And there are a number of modes that SAM has enabled over the years it has been operating on Mars. So of course you can do direct atmospheric ingest and make isotopic measurements and resolve the mass to charge ratio of those atmospheric constituents. You can take solid sample from the surface and evolve that sample through heating, through evolved gas analysis. You can conduct age dating geochronology through the noble gas measurements. You can do atmospheric enrichment of noble gases, of water, of methane through the gas processing capabilities. You can do wet chemistry analysis through the derivatization capabilities that SAM brought on, and you can do combustion of reduced carbon through exposure to oxygen. So this is really a laboratory, right? This is an ambitious laboratory taken to Mars, and given the decade plus of experiments conducted on Mars, the team has really been able to show the power between these, behind these modes. So let's go to the next slide. There's really too much to talk about here, but again, hitting on how important that payload is to establish context for the geological and geochemical backdrop of the experiments that you're conducting on the surface of Mars, informing the discoveries that are not comprehensively listed here, but of course the discovery of sulfur-bearing, CHNOPS-bearing compounds on the surface, the recent discovery of long-chain hydrocarbons, the insight into the chemical cycles, which are so important to understand the seasonal and long-term cycles between chemical constituents and how that plays a role in the habitability of a planet. And then being able to identify, measure isotope ratios, which we know, present with us with signatures of biological activity on Earth, and making, groundbreaking measurements of isotopes. Here is shown the carbon isotopes as kind of a function of the climb or the traverse of the Curiosity rover over its time on on Mars. So it's still going. It is a tween firmly, right? It's about to be a teen. It's not rebelling against us yet. It's doing a really great job there, and just excited to see the continued discoveries of this investment that we've made. Mars, this is maybe not the appropriate time to say this, but I just reflect on how Mars is not one place, right? The planets that we go to are not just one place. It has a geologic history. It has, a fascinating evolutionary history. And so complementing Curiosity, we're going to talk about Perseverance and, of course, ExoMars coming up in the future. So I'll just make that connection here. And then is it back over to you, Aaron?
I think so, yeah.
Great.
Great. So, so Perseverance followed on to Curiosity, but it came with a very different suite of instruments. It had sort of a different main purpose. And again, sort of following more of the chemistry, vein here, focus on a couple of the really chemistry-focused instruments, SuperCam, SHERLOC, and Pixel. But you also want to, caching. Sample handling is one of those very sticky wickets, and the sample caching is one of the most amazing sample handling devices also built, although not directly for in situ instrumentation. Pixel and SHERLOC are an X-ray fluorescence and a deep UV Raman set of instruments. So Pixel is X-ray fluorescence, SHERLOC is deep UV Raman and fluorescence. And it's really, sort of an unparalleled in situ capability for microscale chemical analysis, right? I mean, and they are especially powerful when, overlaid together. And of course, these are a little bit hard to see, but oops, let me go. Here we go. But that top sort of field of view, the kind of the angled white box, if you can see it, that's from Pixel, and the yellow squares from SHERLOC. And you can see you can get the elemental maps off to the right, and then you can start scanning with SHERLOC and getting some of the fluorescence information, and then the detailed spots will give you the Raman and mineral identification. So it's this extremely powerful layered information that is something that has been unique to Perseverance and is a real step forward in terms of in situ development. We always want to be able to do more. We want to get to Heather, but the path is long, right? And so in fact, but you have these breakthroughs, and I think Perseverance was a breakthrough for Raman, right? Raman was something that we really wanted to bring, especially to a place like Mars. And then we got two Raman instruments. We got both SHERLOC and we got SuperCam, being the sort of the worthy successor to ChemCam, which so it has two modes. It has the laser-induced breakdown spectroscopy, and it has the Raman spectroscopy. And so LIBS, this is, Kevin alluded to the fact sometimes we do things on other worlds that we wouldn't do here so much. I think LIBS has become even more powerful, sort of it's cycling back. It became extremely powerful on Mars, and that helped it become more useful here. It's, an extremely powerful elemental analyzer, and then you can sort of reconstruct a lot of that to the minerals. And I think I love the plot on the right there from SuperCam, looking at real-time degradation of apatite over the course of many sols on Mars. And so, again, it's sort of an unprecedented capability up until, these missions. And that's so. These developments are happening. They take a while, but they're ongoing, and so hopefully these next generation missions will have a broader suite to choose from. Also, we heard a great overview on all of this. And we all can lament that if only the mass resolution was slightly better. But I'm going to take the half full interpretation of this, which is like, this is remarkable, right? This is the ability to do grain by grain analysis on a place where you are being given a heterogeneous collection of grains is like mind-blowing, right? So every time something comes in and smashes into there, you get a full mass spectrum. And we obviously we want to collect and get more signal to noise and do, but this is a very uniquely awesome instrument for its application, and will continue, can continue to mature. But it was so fortuitous, obviously, that it ended up on Cassini and had this material to analyze. Okay. Is this our transition?
I think that's our transition.
Okay.
Yeah. So, and
All right.
apologies, like Cassini, it could have been we could have consolidated Cassini a little bit better.
No, we had a great overview last night. Don't worry.
Okay. Oh, cool. All right, great. So yeah, let me take about maybe 9 minutes to go through what's coming up next. So let's go to the next slide. I want to highlight again Europa Clipper. What an amazing mission, a fascinating destination. I think we're all pulling for the great success for this mission. Really, striving to understand what we don't, the many things we don't know, we can model, but really the data, confirming those models will be just groundbreaking for us. So understanding the thickness of the ice shell, critical to laying the foundation for future ambitions and exploring the subsurface ocean, looking at the composition as expressed in its exosphere, and then understanding the geology through a really impressive imaging suite. That has launched, and we're excited to follow it along its journey. If we go to the next slide. Just want to congratulate the Mass Specs team for producing, a really gorgeous, highly capable time of flight mass spectrometer for looking at neutrals in the exosphere of Europa. You can see some of the specs here, and really excited to see the data that continues to help us resolve some of the chemical signatures, especially ones that fall nearly on top of each other in the M/Z parameter. All right, let's go to the next one. Aaron, do you want to follow on?
Yeah, I'll just briefly say that, and that the sort of the legacy of CDA lives on with SUDA, and this will have significantly enhanced capability relative to CDA. It's going to have dual polarity and much higher mass resolution and range, and should if there are plumes at Europa or whatever else is in the sort of the dusty exosphere, we will get significantly improved chemical information out of it.
Excellent. All right, so let's turn to ExoMars. So at Goddard here with our international partners, we've been following the scrappy, persistent MoMA development over its long history here. But this instrument and the rover, are on track to launch in 2028. Very excited to have another highly capable scientific payload, complementary in its application of mass spectrometry, which I'll cover on the next slide, but also Raman and also spectroscopy, in addition to its standoff remote sensing instrumentation. Just a really exciting mission. Let's see if we go to the next slide. It highlights some of the science objectives of this rover. So this is a mission that is explicitly targeting organic signatures for past or present life. Of course, there's since we have the incredible capability of this rover to drill 2 meters, will reveal an entirely new view, an entirely new region of Mars that is poised to provide us with discoveries. So we're building on what we understand about Mars so far from the predecessor measurements, as well as the remote sensing, orbital observations of the planet, and looking deep underground, beyond that damage, radiation damage, penetration depth, to really do a search for those preserved organics. If we go to the next slide. Yeah, I'll just highlight that MoMA builds upon the SAM capability of doing derivatization on Mars surface samples with DMF-DMA, a new derivatization agent for this mission, complementing MTB-STFA exercised on SAM, and not only looking at acquired solid sample that is derivatized and pyrolized, but also looking in laser desorption ionization mode to get at the higher molecular weight signatures of preserved complex organic material. So this is a really capable dual mode MoMA instrument that we're all looking forward to. Let's go to the next slide. So just to highlight here, and I also want to acknowledge, I should have done it before, but the project scientist for MoMA is Will Brinkerhoff, and he is online. So be prepared for me to direct any questions to him on MoMA. But I also enjoy being part of the team back in the day. But just to highlight how the GCMS and LDMS complement each other in looking at the kind of volatile and volatilized elements of constituents of acquired samples, conducting a vertical survey of those signatures as we go deep into the planet at Oxyaplanum, and then complementary to that, the LDMS analysis, which volatilizes more complex organic molecules intact off the surface through laser desorption ionization process. And you see here the calibration compounds that have been used to demonstrate and validate and verify the capability of MoMA. I think there's animation here. Let's click.
I'm not sure I'm capable. Oh, there it is.
Oh, okay, there you go. So here, you just click one more time and you can see
There you go.
some of the requirements that have been verified for MoMA. It is integrated into the rover and ready, getting ready to go. So let's go to the next slide. All right, so exciting, for further development of these dual mode capabilities on Dragonfly, combining, the payload type of exploration, payload level exploration to do characterize these diverse sites on the surface of Titan with Dragonfly, this octocopter that will look at a variety of sites, investigate the microscopic imaging, look at the surface and subsurface elemental composition through gamma ray and neutron, and then comparing that to the mass spectrometry that is really the analytical centerpiece of this mission. DRAMS will be built at Goddard with a lot of overlap from the capabilities that have been built up from MoMA, and bringing again this broad survey of mass spectrometry to explore in discovery mode what we have on the surface, acquired samples from the surface, and then incorporating some new modes in sensitive and selective mass spectrometry to really hone in, target some of the most intriguing signatures that we see in the broad survey to be able to pull out those structures and the detailed composition. I'm watching the clock. Let's go to the next slide. And a little bit more on Dragonfly, so you can see the breadth of access that this analytical capability will provide across its modes of pyrolysis, again, derivatization, and laser desorption ionization, mass spectrometry, reaching into just really a broad diversity of chemical structures and compositions, as shown, kind of represented here as molecular weight, but you can see also the breadth of volatility that is accessible in this really impressive instrument. And I wanted to acknowledge the lead for DRAMS is Melissa Trainer. She wasn't able to join us today, but I know that we have team members from Dragonfly and DRAMS in the room there. And so looking forward to hearing more during the panel that we have coming up. Let's go to the next. Oh my goodness. Well, how could I forget about Venus? Okay, so in one of my other jobs, I am Deputy PI of Da Vinci, the mission to Venus, and we will carry Charles Malespin's Venus mass spectrometer. Now, Venus is not shown to be a habitable environment or necessarily the top target for astrobiology investigations, but what VMS will do, and I'm super excited to be part of the leadership team, will be able to look through a transect of the atmosphere to establish, our basis of understanding and interpretation of a future search for potential biosignatures on Venus. Of course, the cloud region is relatively habitable, relatively clement, approximately Earth-like pressures and temperatures if you ignore all of the sulfuric acid. But really setting the stage for future discoveries, filling in that deep atmosphere knowledge in the history of whether Venus was more habitable, more Earth-like in its past through the VMS investigation and VTLS. So VMS and VTLS, I didn't include a slide here, but getting the band back together from the SAM days to apply to the key questions outstanding for Venus. Let's go to the next slide, and we're running late, so I'm gonna. Oh, Erin, I'm so sorry. There's so much animation on this slide. Just skip through it. I don't think we have time for it. We've gone through, the current state of how we employ these various modes and capabilities in an integrated way to get at the different parameters of a sample that we would like to analyze. Keep going. There's so much. I'm so sorry. Yeah. See, there's more. And now, Erin, we have a whole other set of slides.
Yeah, we're going to beg for 10 more minutes because I'm going to go through those double time so we can get to our questions.
Okay, great. I'm going to stop talking.
Okay.
Over to you, Erin.
Thank you, Stephanie. So, okay, here we go. All right, so that was all preamble because what comes next, right? Sorry, so I'm going to try to go fast, but still give this the obviously what the attention it deserves. So, quickly, right? There are a lot of mass spectrometers. They're getting more and more capable. That's awesome. They provide an extremely powerful axis of identification. As we heard a little bit about in the gas chromatography sense, separation science upstream of them is extremely valuable, and that's kind of a key focus, I would say, of where life detection and deeper chemical analysis is going in terms of trying to enable the standard LC-MS, or more, liquid-based chromatography into your analyzer of choice. And why do you do that? Well, because it's easy. Samples are very complex, and in order to analyze them well, you want to tease them apart as much as possible to have the highest certainty that you have quantitated what you think you quantitated. Okay, and yep, we love mass spectrometers as well. There are other detectors, I'll just say that, but yes, but it's very powerful. 2D, 3D, however you interpret that, it gives you a ton of information. Also, just mention, again, sample handling, critical. It's a pain, right? Some things are polar, some things are non-polar. They want to be in aqueous, they want to be in organic. They just don't want to all do the same thing. And so you have this variety of techniques, and it turns out we care about things all along the spectrum. We can't just ignore one half of it. And so I highlighted the things that are the high level biosignature stuff, but there's a lot of other things. We talked about the context and understanding how that all plays together, and especially how it may be very relevant to abiotic chemistry. Some of those other molecules are critical. And then, right, you can do so much in the lab in order to get at each of these. Again, that flow chart, we didn't have time to go through it, but I guarantee you it had versions of all of these things in there in order to go after different targets. When your limits of detection are not as great as you would like here, we're all about pre-concentration and isolation. All of those things play into that, the challenges that Shannon and Kevin were getting at when talking about, I assume X number of cells and how do I, get down into a biosignature. So I'm going to tell you about one that's near and dear to my heart. Obviously, it's biased towards me, but so this is sort of a summary of, kind of like what are the capabilities we're trying to get to in terms of putting a sample in and getting really specific sensitive chemical analysis information out. This is the Emily project, which Will is the PI of. It used to be the Europa Molecular Indicators of Life when Kevin was giving out IC2 money, and then it became the Enceladus Molecular Indicators of Life when when Matisse was giving out funding. But it's coupling subcritical water extraction with a capillary electrophoresis separation science approach into a mass spectrometer where there's also a separate line to a GCMS. So this is the, kind of going for everything, right? Briefly, SQUEE, it's a pressure cooker. It's it's an Instapot. It's whatever you like. We want to put a cell in and break it down into its constituent molecules. In a life detection suite, you'd like to go look at those cells first before you kill them. But as all good humans, right, we come, we kill, and then we ask, oops, So important things about SQUEE, we've done a lot of work to just sort of say, look, we can preserve these critical distributions that we want to, because you can imagine, like when you make a soup, and it's kind of a heavy hammer approach. But so what you don't want to do is lose that specific distribution of amino acids or of chain length in your fatty acids. And I don't have time, but trust me, you can preserve that by doing it in sort of for the correct temperatures and times. It's also sort of, it's fieldable, right? We've built things. In fact, this was a super cool campaign called ARADS. Atacama, there it is, good. Atacama Rover Astrobiology Drilling Study. So this was, initially, of course, more Mars focused, but this was coupling, a rover autonomously sampling, feeding it into an extractor, feeding that down into a capillary electrophoresis system, and going dirt to data with a real fake science team and everything. Exactly, and Alfonso can tell you even more about that. So, so briefly, capillary electrophoresis. That's our flavor of excellence here. It's an approach where you do a voltage-based separation. You fill a hollow glass tube with a conductive background electrolyte. You add a little bit of sample, and you apply your electric field. You get electroosmotic flow that moves the whole flow towards one end, and then you get your electrophoretic separation within that flow. So it's very powerful, especially for dissolved ions or highly polar molecules. As I said, there are detection modes besides MS. So we couple it to a number of things. Laser-induced fluorescence is an extremely powerful one in terms of sensitivity, which we all know we're concerned with when we're talking about life detection. I just highlighted sort of both MS and conductivity, because when you're looking at abiotic chemistry, there's a lot of other things you can do that are not quite as sensitive and specific as, say, fluorescence, but you can cover this huge space of potentially interesting molecules. We won't reach 16,000, Heather? Yeah, but you can get more things. Just some examples of what kind of, what does this data look like? You get an electropherogram, and, I think many people here have seen this. I won't go too far. We're trying to go through. Okay, so, and so then the Emily concept was, how can we take this as broad a range of these, aqueous, soluble, or organic, and you can think of it in a slightly different chart sort of way. On the right, you've got solubility in water versus heat of vaporization. And so you can kind of get at things which are going to be more friendly to something like a GC analysis or more friendly to something like a CE or LC analysis. And that's how you start to, in one suite, in an end-to-end way, capture as many of these things as possible. Here is our, this was, again, initially we were trying to fit the organic chemical analyzer slot of Europa Lander. And so this was sort of an initial CAD layout of how that might look. And so there's way too much detail here, of course, but I'll just, the LEM, the liquid extraction module, that's a subcritical water extraction approach. You've obviously got a separate cup, an oven cup that can do pyrolysis for the GCMS. It's based around the ion trap mass spectrometer. And then you've got that fluidic sample processing unit, which is one of those important intermediate steps that I want to, if I have, another minute or two to talk about a little bit more, because these are these connecting steps. You got to extract it, and you want to get it to a liquid analyzer, but you'd like to do, if possible, some of this derivatization, tagging it or pre-concentration, et cetera. And so that's kind of a key technology that's been part of this. And these are things that are, really actively being developed, where you're going to be able to do that sample mixing or, dilution in some cases, fluorescence. And there's so this is a version that we've built up that has portions of that capability within the Oceans capillary electrophoresis hardware directly, as well as at Ames, Tony Rico's group has the sample processor. Oh, I forgot to put the SPLICE acronym, but so you've got different approaches for doing this microfluidic handling to take you from your extract to your instrument. Okay. So kind of the brief summary of this stuff is, over the last little while, there's been, I'd say, a shift towards kind of discrete components being built up on manifolds or just through plumbing connections to enable this kind of work. Trying to take the place of students and postdocs pipetting and moving things around. And so kind of all of these capabilities are built in, and they're largely reprogrammable. It's not quite as easy as changing your program on a piece of code, but you can lay out plumbing diagrams and reroute things and enable new capabilities. Okay, so this is my non-exhaustive summary, because it's always hard when it's new technology, because it's changing, but just a brief flavor of what is out there. So BioPow, so this you'll see again that kind of discrete characteristic where you've got kind of discrete reservoirs, you've got a manifold, individual components, and this is preparing to desalt and pre-concentrate amino acids ahead of like a GCMS derivatization. You've got the Excalibur, which is designed to sort of take a bit larger amount of sample, but full on grind it up, do an organic solvent-based extraction, pre-concentrate, and then hand off for lipid analysis. You've got your liquid chromatography kind of, so we've been focusing on CE, but there are also the LC kind of line of development. You've got ion chromatography, which is the sort of specific flavor of LC that looks at ions, and sort of, it's too much to show, but again, it's kind of all discrete component. And then you've got the really interesting supercritical CO2 approach. If you like decaffeination, that's one way that happens. But that allows you to go, again, sort of dirt in, do your extraction with that, and then use that supercritical fluid as part of like an LC approach upstream of your detection. You've got sort of more sensor approaches. So SOLID was developed as an immunoassay. This is from the Spanish group, and that has an incredible actual sophistication of fluidic handling, which I don't have time to go through. And then you've got MICA, which is an ion selective electrode approach, as well as other electrochemical sensors. So where you can go in and kind of, with small amounts of fluid, quickly get a handle on those bulk physical properties, pH, EH, conductivity, and dominant ions. Maybe second to last, we heard a little bit about nanopore, and so you've got both sort of nanopore and I think nano gap, sort of depending on what you call it. There's the difficulty of nanopore is it's sort of, well, it's not living, but it's protein. It's sort of biological material, which there's a durability question. So going to solid state and doing that with these nano gap approaches. But again, this allows you to do these long chain biopolymers and get at things with repeating charge in a very sensitive way. And then lastly, there's MALDI. Stephanie, do you want to briefly go through this? Are you still there?
I am
Yes.
here. I
Yeah.
was giving you the floor. Yeah, I feel like we don't really have time, and that is totally 100% my fault. But MALDI is a way to kind of make the process gentler of laser desorption and ionization to promote even better intact detection of large organic molecules, and that's through a matrix that promotes charge transfer. And if you have questions, I see Sean Lee is online, and thanks, Sean, for your work on this.
Okay. All right. Okay. So now we could spend the rest of the workshop talking about TRL, but I would rather not. So I think that the big picture to me is TRL is, of course, very important. It's the necessary evil. You need some way to attempt to compare, where different technologies are in the development path and whether or not they're suitable for inclusion in a mission. I think, what I would like you to get from all of this development is that these things may be closer than you think. If you haven't, checked in on us in a while, there's been significant development, in these dirt or ice to data pipelines that include the things you need to do, which is get the molecules out, move them around, do something to them potentially, and then analyze them. And so, but the other thing I think it is important, sort of, we got that nice introduction to mission classes. And so, we can think of sometimes very interesting missions that would take use of these technologies to do very specific questions, but they're typically lower budget missions that don't have a lot of room for instruments to go way over budget. And so I would say, sort of generally as of yet, none of these things are quite there to go in kind of a tight, a tight class, right? These are things that need to be picked up by something like New Frontiers or a flagship who are willing to kind of take you that extra level from, TRL 5 through 6 and really have your mission prototype still. Again, I think, but the good news is this kind of, there's a whole conference called MicroTAS, Micro Total Analysis Systems, and those things are amazing, but I think they make it difficult to move up something like a TRL ladder as a community. And so going to more discrete components where you can take something that someone else has sort of shown works in flight and you can use it to base your functions around, it's allowing the community to start to move quicker on these things. And as any good technologist, I just, tech demo missions are important. I know it's tough in a budget environment, but there are a lot of ways where you can, if you don't have it tied exclusively to a pass-fail science measurement, you can get a lot out of that. I think I said all of this. And okay, so our goal, and I think we have, maybe we can push even a little further into the break. Oh, sorry, Stephanie, I thought we were at the panel slide yet. Do you want to say one last word here before we go to the panel?
I think we can leave this up here. I just want to reiterate how important I see the community being to really making fundamental progress on the question of understanding the abiotic background and the intersection and interface to kind of life detection. I think that combining and understanding the environment with understanding, the the foundations of biology as we know it, pushing forward on really agile payloads that allow us to come at the problem from multiple angles, and strengthening the theoretical underpinnings so that we can do a good job of interpreting based on our understanding of the system. I think those are all going to need to work together, and so workshops like this really help us make measurable progress in that direction. So that's all from me on this one. Thanks, Erin. And we do the next slide will welcome our panelists on the stage. So I'll leave it to you as the in-person co-chair.
Yeah, so I'm not sure people need to get up since we don't have a stage. I think we have these throwable microphones, and oh, well, okay, if people want to come up, I don't, please come up. That'll be good too. Just, I feel bad, I make you stand, but here, we'll give you those. So because we have so much, mission and instrument development expertise in the room, we didn't only want to have you all hear us, and we wanted to have some other people up and try to hopefully get a little discussion going with all of your questions. And so we assembled an illustrious panel of a variety of experience levels. And if you all would just briefly introduce yourselves, and then we can, we have some starter questions, and then we'll go to the room.
Okay, yeah, I'm Frank Postberg from Berlin, and my main expertise actually in terms of instrument development is from CDA and then further on to SUDA and future mass spectrometers. That's my link to this in situ experimentation panel.
I'm Jen Stern. I'm at NASA Goddard. I am a member of the SAM team and the Curiosity team, and I am also the lead in the development of the gas chromatograph for Dragonfly mass spectrometer.
I'm Bethany Teeling. I'm also at NASA Goddard. I work with Erin actually on the Emily project, which is now extraterrestrial. Yes, so yeah, we just keep going. Moving targets, right? So I'm actually the lead on the GAPS, which is the GC side of that particular instrument suite. And I also do a lot of AI and machine learning on board.
I'm Ashley Hanna. I'm at the University of Maryland. Is this one on? Can you hear me? Okay, cool. I'm a graduate student at the University of Maryland, and I primarily focus on studying how laser desorption mass spectrometry can be used to identify microbes.
Hi, I'm Zika Asher. I'm a postdoc in Heather Graham's group, and I'm working with agnostic biosignatures, with mass spectrometry, and mostly GCMS.
Great, thank you all. Okay, so I think our first question will be for Frank and Jen, and it's sort of, what have you learned from operations or late stage V&V that, if you could feed it back to the beginning, that, as earlier on in the instrument development, that you're like, these are things that, you may not have the time to think about, but you really should if you can.
Okay, there I have to leverage my Cassini experience, and the important lessons there is stay flexible, right? Adapt. I mean, of course, you have your science traceability metrics and you optimize your instrument to certain conditions, but you will always be surprised. And Cassini showed that it could react, totally change the entire mission and the goals, and the instrument were somewhat flexible enough. But yeah, and from CDA to SUDA for Europa Clipper, we clearly learned some hard lessons with the instrument limitations. And SUDA is much more flexible now to adapt to specific conditions or new measurement goals that pop up. It's like for exceed the mass range or have a bigger room for data storage. So just more flexibility, I think, is important, not just focus on, yeah, I have a super high detection limit for certain amino acids under certain conditions. No, that's not the approach, I guess.
I think I would have to say, know your ConOps from end to end. So know your concept of operations, early on in your development. So you think about, if you work in a lab, you inject a sample into a GC and out the other end comes your data. You really have to think as you develop from the point where you collect the sample. There's certain requirements, whether you have to keep the sample cold or there's a range of requirements, and that sample has to make its way to through processing systems to your detector. And so you really need to think about every single step of the way, including, okay, maybe this part of the instrument needs to be heated and this part of the instrument needs to be cold. That can be a really technical challenge, a big challenge. So at the beginning, really thinking about that experiment that you want to do and thinking about it from end to end.
Okay, next, maybe Bethany, do you want to comment on, where do you think AI or ML is going to, really have the largest impact on instrument or instrument development, in terms of there's obviously the data, there's operations, there's fault detection. We already heard that it helped Frank yesterday, and we know it helps Curiosity. So,
Yeah, and I actually, this was a great introduction to what I wanted to talk about with that, because I think that we can use AI and machine learning to develop adaptability. So, I mean, we've been able to do incredible things in space with just resources that we planned very, very carefully. And I think that by knowing your ConOps and adapting, we can use AI to adapt to that. So the work that my group is doing at Goddard, we're developing this onboard AI system. I presented a taste of that at AppSciCon a few months ago, but we have done so much since then. So I'd love to talk more to people if you're interested. But a lot of that is taking your ConOps and then feeding that into a matrix where you can start making decisions and you can actually adjust the interest level. So let's say at the early part of your mission, what you're really interested in is exploration. I don't know what's here. But let's say that you start collecting data and you learn things about that data. You can learn on the fly, and then you can adapt your models on the fly to do something different. And so I think that that's where I see a lot of this going, is that we're going to have the power of adaptability in space. So I think that then I was thinking about the what is it, dirt to data, and I was like, oh, well, we could do dirt to data to decision making to discovery. So that's my transition line. Yeah,
we already have to reprint the shirts.
I know. Adaptable.
Thank you.
Mm-hmm.
So then for Zilka and Ashley, you're obviously at the stage where you're doing a lot with your hands in the lab and all of that. So what worries you about taking these methods and things you're developing in terms of getting them onto robotic in situ exploration?
Yeah, so I'm always approaching these questions really agnostically. So I don't want to look for specific molecules like peptides or amino acids. And with that approach, there is a big issue with the molecules I'm usually interested are slightly bigger. Often they don't necessarily are volatile enough to directly put them into a GCMS. But if I prioritize them, I change them so much that I actually don't quite know what I'm looking at if I go abiotically. So I'm a big fan of sample return in that sense, because that solves a lot of problems if I can put it in an LCMS. So that's a big challenge, definitely.
And I'm probably just going to reiterate a lot of things that have already been said, but machine learning is going to be one of the challenges. Convincing people to fund that work and to get it on board, having bandwidths that are capable of sending back enough data to implement algorithms on the ground, but then also in situ. And then I also work on MALDI mass spectrometry. Right now, we're not planning on sending MALDI, the matrix-assisted laser desorption power, to another planet, but if we could, that would be great. But that does incur sample handling risk and then risk of the instrument, potentially for contamination and then more cost. So those are things that I see as challenging.
Great, thank you. And so we'd like to open it up to the room for people, for our panelists, or for Stephanie and myself as well, if you have questions. Can we throw one of those to the crowd?
And I see a question online too that we can come back to.
Oh, we have, sorry, thank you. If you, Stephanie, interrupt us after this one in the room, please.
Okay.
Hello? Okay, it works. I guess maybe this, oh yeah, hi, I'm Marshall Seaton, JPL. I guess this may be a question for Aaron, and maybe a bit of a technical question, but I guess liquid sample processing capabilities, onboard liquid sample processing capabilities have been in development for quite a while, and it seems like obviously not a ton of that has flown yet. And that's presumably because there are a lot of difficulties in elevating the TRL of such systems due to the complexity and some other things. And so I guess a question of what are some of the big barriers and the hurdles that we have to jump to ready the liquid sample processing capabilities to where they can be like routinely flown in flight, and that we're confident that we can implement those technologies?
That's a good question. So, you know, I will highlight that there have been some of these things flown. It's been mostly CubeSat, right? But again, the group at Ames has put together some of these biological CubeSats doing mostly experiments towards radiation exposure, though, where they've had, you know, fluidic cells move things in and out and do those exposures. And so I think the biggest challenge is sort of, I think, at the system level, which is that fluids, you know, as we analyze them, prefer, you know, lab conditions, right? They prefer lab ambient, and sort of maintaining lab ambient or thereabouts while doing these fluidic conditions is an engineering challenge that has led, you know, sort of led people to develop a variety of different approaches. So instead of driving ahead on one particular approach, you kind of have a plethora of options, which is a natural thing. But I think that weeding out of all the different ways you might do this until you get to the one that's really going to be the most robust and applicable to space instruments, I think that's the underlying process that has taken a while to get there. And again, I would advocate that the way a lot of people have independently converged on discrete components, you know, basic plumbing or manifold plumbing, and then allowing that to do all of that is what's going to take us to routine use, because you want to be able, you don't want to build it once, and you want to be able to say that was nice, but like the mass spectrometers where they've built on their developments, we want to be able to, you know, do it once but have the next one in the pipeline as well.
Awesome, thank you.
Can I suggest that maybe, Aaron, does anybody on the panel have perspectives on that from either their area of expertise or involvement in current development?
Expertly said.
Okay. Yeah, and I agree, like the sample handling and the sample integrity and maintaining the sample as pristine as possible is key, right?
Sorry, I cannot. Okay.
Did I go to the online question?
Yeah, okay. Okay, so the question online is there one specific measurement technique that could create a significant impact if the measurement accuracy got improved? I asked that from the perspective of an engineer, thinking about where a technology leap could be the most impactful. And that's from Paula do Valle Pereira. Excuse me. Yes. And I think that's for the panel. So if you pass in the book.
Well, I'm going to be biased because I'm an isotope geochemist, and isotopes are typically, precision is what you go for with isotopes. Of course, we would love to see better accuracy because it would probably not completely negate the need for standards, but if we had something that you know, could accurately measure a range of isotopes and maybe not just one or two, I mean, that would be beautiful.
Can you?
Okay, I'm not going to try throwing these.
Aaron, was it me or someone behind?
You can start, and then there's behind you. So.
Do you want to go first?
Woo, good throw.
My vote for instrumentation would be high accuracy, high resolution MS. And I'm done.
All right, Morgan Cable, JPL. I'm going to ask a TRL question because as we've all heard, there are so many that are in development, TRL 2 to 4. Yep, that's great. And then there's a cliff that happens around 5, 6. And I think this is sort of exemplified in a bit by Dragonfly, right? DRAMS is, we're actually pumping it down to Mars surface pressure to do the LD side because that part has already been, demonstrated embedded. And so my question is, as we are developing new instruments, to get to TRL 6, you have to demonstrate it in a relevant environment. But are there ways that we can include multiple relevant environments when we first do these tests to get to TRL 6 so that the technology could be applied to other potential bodies without having to go through that entire process again?
Interesting. I mean, that would be great. I think starting with sort of TVAC, doing it at vacuum is always sort of the nominal way. So, but yeah, I mean, it would be great to earlier on be able to, validate for other environments, because you might find out something really doesn't work, and something might be a deal breaker. I don't know if the funding exists for that, but it's absolutely true. I mean, you can run into a deal breaker, and then you wouldn't want to go any further with development.
Can I add another oh, Bethany, go ahead.
Go ahead, Stephanie.
Oh, I was just going to add the perspective that, often we're working to cost caps on these missions. And so it can be, prohibitive to test instruments like this under a variety of environments. But Morgan, I guess your question is along the way during the development. And I think it's an interesting question to ask because of the TRL definitions and the reality that the environment really does matter in the operation of this instrumentation. I would just caution, like the case of LD, ambient environment, it may change your solution, right? If you require your technology to operate under such a wide range of environmental conditions. But that's useful to know as well, right? Sorry to step on your toes, Beth.
Yeah, I would just say, it also comes down to how much you want to manage the spacecraft environment to keep it, along this sort of, tolerance and margin, so that's the other way I think of addressing that, which comes with its own cost, of course. I see Steely back there with his hand up. Yeah.
You've got the box and then back.
Oh,
You all hold on to the box. You all hold on to the box. You've got a question,
Yeah,
and then Steely.
I want to follow up. So David Boulesse from University of Florida. I want to follow on the first question. With Emily, we did a GCMS ETU campaign, and apparently we might have done liquid chromatography, or at least fluidic chromatography or fluidic analysis. Might it be like a clue to get this TRL passed thanks to ETU campaign where we couple, like for Emily, GC and other fluidic components?
I just want to make sure I'm getting the question right. So I think the question is, can we combine a bunch of different
like
parts of the
Emily,
campaign?
you did it, and would it help to increase the TRL?
I think so. So I think I feel like that's probably the way that things are going anyway, because I mean, it is so expensive, as Stephanie pointed out, it is so expensive to do these, TVAC testing campaigns anyway. So I think we are trying to make sure that we combine components as much as possible instead of having I think the original plan was to do a bunch of separate ones and then combine them. And I think now we're like, let's just accept the risk and combine them and then do the campaign. So that is a mechanism.
Right, it goes back to that ConOps again, going end to end and understanding how your sample is changing and being delivered.
And did you do ETU campaign with the liquid part, or it was just with the GC part for the Emily?
You didn't have liquid in your.
We did
Yeah,
not,
you
no.
just did
No, we
GC.
just did volatiles, yeah.
Andrew Steele, Carnegie. I'm struck by this because 20 odd years ago, I started working with the Spanish on the life marker chip. In fact, prior to working the Spanish doing this, we got this on ExoMars. We started doing all the liquid handling. We flew a microbial detection system on station using fluidic handling systems. We're here 20 odd years later, and we're still discussing how we're going to put fluidic handling systems up. Now, it starts with your sample. If you're going to a rocky planet, you need some way to get it off rock. If you're going to an icy world, you need to deal with that liquid, etc. So my question is going to be extremely provocative. Break the entire system. Start from zero. How would you put together a system to make instrumentation to undertake these analyses outside of the current NASA, ESA way of doing things? Getting into more commercial or even private funding or even entrepreneurial funding to do so, because we are here 25 years after the life marker chip was first put together for ExoMars. It was booted off, and nothing's changed. And I don't want to be here, well, I won't be here in another 25 years, but, and going back to the sample return thing, I hear you, but we are extremely good at making miniaturized instruments. Why aren't they flying?
Well, I agree with your like rethinking stuff. And also like a lot of instruments that we currently use are like made for not necessarily ocean worlds, because if you think about liquid chromatography, like on an ocean world, we have water, like there's no instrument that kind of like can leverage that right now, I guess. But if we rethink things, we might actually have resources, like salt will then be the problem, I guess. But yeah, it's interesting.
This also might be provocative, and as the graduate student, I'm gonna say it. We seem to avoid risk a lot. And I don't understand when the whole idea is to do risky things. But if we keep sending the same GC over and over again, I'm not sure what else we're gonna learn.
Yes. I'm so proud of you. Thanks. That's exactly what I was going to say. I'm so proud. I'm so excited. Thank you. This is awesome. No, yeah, I totally agree. Like we have got to start accepting more risk. And I think that the way to do that is not through a flagship. Like you're just not going to spend like $5 billion to send a spacecraft to Enceladus, like a flagship to Enceladus. It's just not going to happen. Like I think as a community, we have to start getting really creative. And maybe we do need to break everything and just say, what can we do in a discovery cost cap? Like, and I think that we need to stop saying, oh, I'm gonna send, I'm sorry, Goddard. We can't send like the same exact mass spec. We can't send the same exact, like everything, imagers. We have to, like, we really do have to break it. And I'm so excited to see like early career people here. Like you have the opportunity to not be bound by the same rules. And I want to see you do that. So please do. I'm willing to accept more risk. I think there's plenty of people here who are, so let's get together and do it.
So,
yeah.
So as an early career who has, I mean, we're going towards Dapper, right, in our proposals, but how do we get people to take that risk when they're selecting?
I think that's a great question. So the headquarters people who might be listening or upper administration, that is really helpful because I think that needs to happen.
Sorry, this is actually really well. Okay, so Kurt Niebuhr just gave an update for the next New Frontiers, which he's not calling New Frontiers 5 anymore, right? It's just New Frontiers now. But he did state that there's going to be a percentage of the cost cap for a technology development that is not meant to be a TDO. So it's not a technology development option that you just sort of append on, but is not actually critical to your science. This is something that's supposed to be crucial for the mission that could be on the order of, say, $5 million or something. So I think headquarters is listening and they're doing their best to try to implement ways that we can include higher risk technology elements in our concepts. I thought that was important to note.
Thank you.
Yeah, I'll just add one thing about, here we are 20 years later, but so the risk is not only programmatic or technological, it is scientific, right? If you demand essentially the performance that only a liquid chromatography mass spectrometry system can provide you, you will end up building very slowly a miniaturized version of that. I mean, and I think LifeChip was trying to break the paradigm on that, and it didn't succeed. But if you have to be willing to say, well, we're going to try this. It may not give us the scientific return but it also may open up something we didn't expect. And so, discovery-based science as an acceptable approach to missions will also open up or not open up those sorts of things.
Let me add, can I add? Somebody's speaking in the room.
Just putting suites of instruments together that naturally talk to each other is also not part of this. Everyone's got their own instrument, they don't talk to each other. And the whole thing is a competitive one to the point where it becomes really quite personal. And it can be very, 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 stressful for young career scientists to get involved in a shark pool, basically. And so I want to see more, hugs, if you wish, but I want to see more people come together because no one instrument is going to make this measurement. It's got to be a suite of instruments. It's got to be miniaturized. It's got to work together, and it's got to be led by.
Yes, I'm so excited that you brought that up because because the AI group that I'm working with, so we're actually developing the capability, we've already developed it, in fact, the capability for extensibility. And so what that means is that you can actually call in different assets. So we're trying to basically build something that's like, effectively the analogy is like your iPhone and your Android can talk to each other. So they weren't built to talk to each other, but they can, right? So we're trying to do that with different instruments so that you could have like maybe a really high risk instrument and this like low risk instrument and an instrument from a university and an instrument from an industry that were never actually built and designed to talk to each other, but they can. So we're actually, we delivered the code, I think 2 weeks ago, and we're like flying it in a tech demo in a couple months. So we went from TRL 1 effectively to 7 in just a few months, which is really exciting. So like things are going fast. So I'm so excited. Yeah.
Jen,
Okay, I'm going to follow up on a few things. This is Jen Eigenbrode, Goddard Space Flight Center. First, I wanted to mention that Steely, there is a program called the Small Business Research, Innovative Research, that does really promote getting our commercial sector and independent research groups to come up with these creative ideas and work with people in NASA to try and make sure that they're developing along the lines where it fits most of NASA's needs, including, making sure it works with spacecraft and all the environments that has to go through. Yes, okay. So I just want to point that out, that it does exist. And a lot of us in technology are engaged in working with those groups. So there is a path. The other one I was going to say is on GCMS, part of the reason why I think GCMS has flown so many times is because we have 80 years experience. And that doesn't mean that there are not other things that we can do, but we have so much familiarity with that and have so much experience looking at a wide range of chemicals using those techniques that we feel comfortable with it. So we have to build the familiarity with the instrumentation for a lot of samples in order to get to the same point.
I definitely don't want to take away from how powerful it is. It's very powerful. So I did want to make that addendum.
Okay, the question I had originally was, so there has been a lot of progress on understanding contamination transport in space environments, but also in the facilities like the launch vehicle processing facility, on the launch pad, during launch, during each episode of cruise, EDL, landing, you name it. We're even talking about maybe doing contamination transport of molecules within instruments. And what we're talking about is more or less organic molecules that move around from surface to surface or change. And how does that happen? Well, you use computational flow dynamics, you use all the physical conditions, everything you do know that you have data for to try and model it. So my question is, do you envision AI helping us with this?
Oh,
Because I think
absolutely.
that when, and after everything that you mentioned, Bethany, was that what if, we start seeing things in our spacecraft instruments, and now we're starting to wonder, well, where else could it come from? And is there a possibility that we might use this kind of transport modeling to understand if there is a possibility it came from us, that we brought it with us, or if it moved around and, or no, it's not likely, I'm just wondering if that would fit into the decision-making
Absolutely.
aspects.
Yeah. So the way that we're building it is that you could use it for whatever purpose that you want, because we recognize that you can't do everything. Probably there's not the computational power. I'm really excited to hear about like the high performance computing that headquarters is really trying to promote. So I'm really excited when we get that. I want to play with it. But I think that that's one of the things that would be really, really useful. And it's like, these are like the low hanging fruit, right? It's like, could you have really lightweight model that you develop on the fly that's like, oh, this is part of my instrument. So like during your checkout, even during your cruise phase, you could start doing these sorts of things to be like, who am I? It's like the hello world sort of part of it is like, you could develop that. And right now, I know a lot of people are like worried because these AI models are huge and they require lots of power. Ours do not, and you don't need to develop these really heavy models. Something like a contamination transport model, or even just a classification model for that we're running those on Raspberry Pis. They're super lightweight, so we can do that right now already. So I think that like if that's something you're really interested in, develop that model and like let's fly it. Let's just do it. Why not? Let's do a tech demo. Did you want to like add anything since you're
Okay,
actively
so
working
we
on
are
this?
we're running into lunch now, so I don't want
sorry.
to no, but let's thank the panel.
I
It's
have
been
one
great.
more. I'm sorry, Aaron.
Oh,
Co-chair's prerogative. I'm so sorry.
oh yeah,
I
yeah.
have to say,
Take it away.
I wanted to emphasize how much investment and development, Aaron, you showed, and the Emily team has demonstrated in developing the maturity level of the liquid handling capabilities. And I realize, as with all of you, that there is a randomness to the connection point between that development effort and the mission that flies it. But I think that the investment that's been made by the agency and the really hard work by the teams in the lab, demonstrating prototypes, demonstrating environmental performance. This is all moving us forward. I know it's not very predictable and it's kind of nonlinear, but I am still optimistic about it. The other thing I wanted to mention, I'm sorry, I'll be brief, is that, there was a comment about always flying the same instrument. I get that. As someone who loves to see like cool new advancements in technology applied to the problems that it solves, that's awesome. I also want to highlight that there is sometimes innovation and importance to answering targeted science questions with instruments that are well understood. So a portfolio has to be balanced, I think, to be responsive to the budgetary environment and the ups and downs that we live in. So I just wanted to make that point. But I think we're all in this together, and it really requires a diverse portfolio to achieve these big goals. So anyway, thank you, Aaron, for being my co-chair. I'm going to go back off mute. On mute.
Embrace planetary protection early and often.
Okay, thanks again, everyone.